Какую? Да.
Там есть что-то?
Я просто остался в движении.
Там уже все было готово. Тут надо было найти научку.
Нет, не так круто.
Сам круто.
Я там не понял.
Нет, ты где сидишь? Это сидит уже, да? Днем, а тут никто не сидит. Давай, это что?
Так, кому стульев не хватает, можно аудиторию высказать.
Да. Да. Понятно.
Аудиторию можно взять.
Это все правильно.
Okay, let us begin. It's 6:45. So welcome everybody to our first seminar in this academic year. Congratulate all students for the beginning of academic year. This is this holiday, but not only for you, for us as well. Okay, so let's just perform personal checking for group members. Third year students, raise your hands. And third year students. Where is the other? I'm here. Okay, why don't you raise your hand? What year students? 3 year students. Okay, 6 year students. 3 year students. Where's Sergey? You consider it as Why is it PhD student? Until you get your PhD degree. So today's talk will be given by Dmitry Molchanov. It will be about some intermediate results, some work in progress on deep Bayesian methods, so an application of variational Bayesian techniques to linear models and some preliminary results to deep architectures. That's, from my point of view, quite promising area, since several heuristically based regularization methods have been recently explained using Bayesian framework, and this explanation provides us new ways for building even more powerful regularizers. This is why it's quite important to study this direction, to study the potential of application of Bayesian regularization techniques to deep learning. And this is one tiny step towards this direction. So hopefully, it will not be the last step. Hopefully, it will be more or less interesting.
We consider several neural network. So here is a custom layer. We have input, we non-linearity here, and okay. So what is Dropout? Dropout is a common regularization technique, which works like this. We have a binary mask here multiplied by input and then multiplied by the weight matrix and have the result. And this matrix is set of boundary distribution. Each is the Dropout range. So Dropout helps to prevention fishing. So like here you can see the examples. So these two networks are trained with Dropout. It is a test classification error. And these two trained without Dropout, and they are. However, binary Dropout is pretty slow and it is intractable, and it is some kind of heuristic. So the next thing is Gaussian Dropout. So when we use binary Dropout, we need to modify the network driven testing. We need to scale the weights like this because they drop like this given training. And it is the same as if we applied this scheme to training. So here the expectation of this new noise is 1, and variance like this. And when we instead of using binary noise, we can use Gaussian noise with similar mean and variance, which should work the same as the binary Dropout. So
what is the motivation for using Gaussian Dropout? So more flexible?
Yeah. So like it is a continuous module, not so there are no binary variables.
And probably one explanation of why we can do this is a reference to central limit theory.
Yeah.
That if we have many different binary noises, this is in some sense equivalent to Gaussian noise.
Yeah, because we still have a linear combination at the end. So another thing that we can do is to look at Gaussian Dropout and see that as this thing is Gaussian, and these are some linear combinations, it means that matrix B is also under Gaussian distribution with some more difficult parameters, but they can be computed. And now we can sample the actuations instead of sampling the null matrix. So networks with this approach, they converge faster because the gradient of, well, the gradients have less variance, and the results should be the same because, like, the distribution of activations is the same as with binary dropout. However, in reality, this technique can lead to overfitting because still the variance of the gradients is smaller.
Is this your observation, or you found it in some papers?
It is both our observation and I think it was mentioned in other papers, like fast dropout.
So this is quite interesting effect. We have the same function, the same criteria which we try to optimize, and it appears that if we use stochastic optimization, if we have a stochastic gradient with a small variance, this is worse than stochastic gradient with a greater variance, because the small variance we have, the stronger is overfitting effect. This is quite counterintuitive, but this is what happens in reality.
Why is sampling acceleration faster than sampling noise?
Like faster in the sense that the convergence is faster. Not the epochs, but the convergence.
It corresponds to sample separate weight matrix for each object. Instead of sampling a lot of matrices, we can sample only activations.
Okay, and this thing here leads us to variational dropout. To obtain this distribution, we can follow a different way. It is the same as if we have this form of distribution on the network weights. So if we substitute this thing into like here, so this is weight, we obtain the similar distribution, the same distribution.
Could you please explain your notation once more? What is theta?
Okay, theta is a parameter that, in a sense, it is the mean value of network weights.
Which is assigned by whom? By user, by algorithm?
Actually, this is the parameter which is tuned during training. So this is point estimate of the weights. And the weights, Wij, are now treated as random variables which have specific distribution. Parameter alpha is fixed, and parameter theta ij is a point parameter which is tuned during training.
Yeah, so like here, W is just a number, so the W here is, we can say that it is equal to theta, and here W is a random variable. So yes, alpha is the new like dropout rate from Gaussian notation, like here. So it is a dropout rate from Gaussian dropout, and it corresponds to B with this.
So there's one-to-one correspondence between alpha and dropout.
Yeah. And if you have large alphas, it means that like alpha goes to infinity. It means that the dropout rate is close to 1, and like we drop this weight on all iterations. And dropout rate and alpha equal to 0 corresponds to P equals to 0, so no dropout. Okay, so is this correspondence clear?
What is B here? BAK.
B are the elements of matrix B, iterations before nonlinearities.
And where is the bias term then? Do you have it?
No.
Just simplicity.
Yeah.
So the last equation is simply the reparameterization.
Yeah.
So you have a generator from standard normal distribution. This is how you do in order to perform this additive correction, this additive addition of a random variable.
Yeah. So if we have this distribution, here comes the idea. Let's use this form of distribution, this family, to search for an approximate posterior for the network weights. So this will be our variational distribution.
And what we do in testing phase?
In testing phase, so we can sample doubles from this distribution and then
Sample. So
We can say,
our
we
answer
can use
is
it as a
stochastic for a particular object.
So ideally, we would want to average the result over this distribution, but we could use a point estimate, like theta.
I didn't get what you said about the variational distribution or something.
Yeah, so this distribution, like it is a it gives us a family of distributions with this parameterization. Like the mean is theta, the variance is alpha times theta squared, and we search for our variational family is this.
Let me try to clarify. So now we're trying to switch to Bayesian framework. And under Bayesian framework, there is some prior distribution for the weights W. And during training, we perform inference, and we transform our prior distribution to posterior distribution. Of course, since the model is too complex, we can't do this explicitly, so in an exact manner. And we have to perform some kinds of approximation. And the variational Bayesian inference provides us way of how to perform approximation for the true posterior distribution. To do this, we need to fix some parametric family of distributions. And this is the family that we have fixed. So we will search for posterior distribution for the weights W in the family, which factorizes with respect to all Wij's, right?
Yeah.
And each factor, Q of Wij, is parameterized by parameter theta.
Yeah.
So we now imagine that alpha is fixed, because alpha corresponds to dropout rate, blah, blah, blah. And the only degree of freedom is theta. So by tuning theta, we will tune our approximate posterior distribution. And this is what Dmitry meant when he told that we'll use Q Wij as a variational posterior distribution.
Yeah.
And now the questions are, first, what criterion should we optimize in order to this approximate posterior distribution? And second, what is prior distribution here? Right? Because now we had no prior. We had just a dropout procedure, which is some heuristic procedure. And the question is to relate this heuristic procedure, dropout, with some Bayesian inference. So we're now planning to show equivalence between these procedures. And to show it, we need to fix prior distribution, and we need to fix what criterion we optimize when we try to search for theta Ij.
Yeah. Yes.
And before we go further, can you repeat please what is matrix A?
Matrix A is just the input of this layer.
Oh, thanks.
Yes.
Why do you use this particular variance here? Alpha times theta squared. It's kind of counterintuitive for me.
It is counterintuitive, but this notation gives you this. So it is the only way to obtain this distribution.
Why do you want? Oh.
Because this distribution, exactly the distribution which we obtain when we use Gaussian dropout, and approximately the same distribution when we use traditional dropout. So again, we're trying to relate Bayesian techniques to already existing regularization techniques.
So yeah, we want to build a model that when the alpha are fixed, that this model is the same as Gaussian dropout. So okay, what should we optimize? So we want to minimize the KL divergence between our approximate posterior and true posterior. And in order to do this, as usual, we maximize the variational lower bound. Yes?
Are you sure that, well, I understand that these two problems are good, but are you sure that we are interested in minimizing the KL divergence? Because we optimize with respect to theta, which both are included in the posterior and in the approximate posterior, right? And
No, they're not included in exact posterior. They're not included. J are the variational parameters.
okay.
They only define our approximate posterior Q of W.
The variational lower bound, alpha, evidence lower bound, each has the following form. So this is the expected of likelihood, the expectation with respect to the variational distribution, minus KL divergence between the approximate posterior and the prior distribution.
T is what was B on the previous slide, right? It's like the
What?
output layer. T.
T is yeah, so it is the output of the whole network, and X is the input, the very input.
So could you interpret it as some kind of regularization of training procedure?
So yes, we have like our likelihood, and we add some regularizer.
So just imagine what happens if we remove the second term. So you have just the first term, and if we want to optimize it with respect to Q distribution, then we will definitely end up with a degenerate distribution, which is delta function at the most probable point WMP or WML. So this is standard maximum likelihood procedure, which suffers from all these drawbacks like overfitting. So in order to prevent it, there is a regularizer, and here regularizer is quite natural because it arises from the shape of evidence hour bound, and this is scalar divergence, which penalizes difference between prior distribution and our posterior distribution. So it prevents us from ending with a delta function. So this is why these two terms, the first term can be interpreted as data term or error, training error term, while the second term can be interpreted as a regularizer, which prevents us from overfitting.
And which prior do you use in weights?
I'll talk about translation on the next slide. So now, except for the prior, the model is fixed. We can treat both alpha and thetas as variational parameters. So now we can optimize alpha with respect to alpha 2, not only theta. And we can use the same alpha for all the layers for the whole network, or we could use unique alphas for a single layer, for a single weight, for a single neuron, etc. Is this clear?
Let me again try to clarify it a bit more, if I can. So how traditional dropout works? We do not have any kind of scalar divergence. Our value is just log likelihood of training sample. And we try to optimize it with respect to what is noted here as a theta ij. So no Bayesian regularization, just some heuristic procedure. Now you want to reformulate it in terms of optimization of some Bayesian criterion. In this case, this is evidence hour bound. So we know that dropout corresponds to, and especially in its Gaussian notification, corresponds to such kind of normal distribution with theta ij as a mean and the alpha theta ij squared as a variance. But alpha is fixed. So in dropout, you only optimize with respect to theta ij. Now I understand that since both of these parameters are parameters which define approximate or variation of posterior distribution, then in theory we can actually optimize with respect to both theta ij and alpha. And this immediately provides us way for automatically setting dropout rate and even setting different dropout rates for different layers, for different neurons. But the problem is that in order to obtain this R bound, variational R bound, we immediately have to add to subtract this scale divergence, which was missing when we used classical dropout. So now there is some kind of divergence. And what Dima will do next, or will tell next, he'll tell how to set such prior distribution P of W that it does not depend on theta ij. Because if it doesn't depend on theta and ij, then if we fix alpha, we immediately obtain the same procedure as in the standard dropout or Gaussian dropout, right?
Yeah.
So, and since in these standard methods nobody optimized dropout rate, they could simply ignore the last term, the Hell divergence. Now we will set special kinds of prior, such that Hell divergence doesn't depend on theta ij, but depends on alpha. And with this term, we can now optimize both with respect to theta ij and alpha.
Yeah. So, okay, and we have this expectation here, so we can't just take this expression and compute the gradients, but we can use the reparameterization trick. So, just like on the previous slide, we can use the new value of W, which can be computed like this, and substitute it. So, so-called reparameterization. And after that, the expectation will be taken with respect to standard normal distribution, and we can compute. So the gradient of this expectation will be equal to the expectation of the gradient. So there will be no problems. And the Kyle divergence, there just will be an analytical expression. Okay. So for this optimization to be consistent with dropout, we need to find such prior distribution so that Kyle divergence does not depend on theta. So that if the alpha is fixed, we optimize the alpha with respect to theta. It should be equivalent to optimizing the expected log likelihood with respect to theta.
So recall how dropout training looks like. On each iteration, we emit several neurons by random and make step towards stochastic gradient, right? But this random emit sum is equivalent to just taking stochastic gradient of this expression, of the expectation of log likelihood. So this is the key observation which was made by probably Max Welling and his co-authors. But if it is so, this means that actually there's no dropout. We're just stochastically optimizing such kind of expectation of log likelihood with respect to distribution Q, which is given by this normal distribution with a mean theta ij and the variance alpha theta ij squared. Until we do not optimize, until we start optimizing with respect to alpha. So if we do not, then these two problems are equivalent. But now we would like to optimize with respect to alpha as well.
Excuse me. So is this correct that if you use this so-called standard the procedure which is equivalent to the standard dropout training, then you do not try to set weights to close to zero because there is no term which is would do that in your objective.
Well, if the alpha is fixed?
Yes.
So yes, if it is fixed, so we can just exclude the Kyle divergence from our objective, because it will be just constant with respect to theta, and here we have this procedure that is equivalent to
There will be no sparse supposing.
Yeah.
Okay. And why do you believe that this may be better than the full procedure with Carroll divergence?
No, we need it so that we will optimize with respect to alphas 2, but we want this model to be as close to dropout as possible.
Yes, and what is the motivation for this?
The motivation is we
To justify the dropout procedure. Because the dropout procedure is now heuristic. And now we're trying to justify it and say that actually this is just a rough approximation of Bayesian inference with a special kind of prior. If we understand this, then we immediately can change the prior and we will obtain different procedure, which we could not obtain from dropout.
Yes,
Yes,
but I'm just confused because you already had the variational dropout, which is a more general case of standard dropout, probably. And you already can change different priors in it.
This is just a reproduction of variational dropout. There's nothing new here.
Okay.
So yeah, we want to obtain the model that so the standard dropout is a special case of this model. So if you take variational dropout and fix alphas, it will be standard Gaussian dropout.
Please repeat why KL doesn't depend on theta.
Why, like,
Because Q depends on theta. And so KL also should depend on it.
Unless we establish a special kind of prior distribution.
yeah. So,
So we now try to find what a prior distribution should be. That Carroll divergence doesn't depend on theta.
yeah.
Again, we're trying to solve reverse problem. So we have dropout procedure, and we would like to build such kind of Bayesian model that it corresponds to dropout.
Yeah. So in the variational dropout paper, in the original paper, it was discovered that the only prior to satisfy this property is a log-scale uniform prior, which looks like this. So, and the corresponding algebra difference is an expression that looks like this. So here we have only chunks that depend on alpha.
Could you please write down the black of why dependence disappeared here?
Okay. We consider one-dimensional case. So our approximate posterior is looks like this picture. Alpha theta squared. And
Could you please change marker
on
on the theta one?
okay.
Looks like a variational dropout.
They're all the same.
And the ones which are located on the table,
Oh,
it should be better.
yeah. So, okay. Q. Q. Okay, I don't quite remember the expression for Q of W.
Q of W is proportional to 1 over W.
Oh, yeah, okay. Yeah. W, and which is proportional.
And the integral is vector W.
Yeah.
And now we need to show that this expression doesn't depend on
Yeah. Right. So.
So probably we'll split logic into two parts. I want to show that the first part is simply entropy of normal distribution, and the entropy of normal distribution doesn't depend on the mean and depends on the variance.
But variance depends on.
Yes, but you got
Okay.
you also have another term, which will be plus log of W, and expectation with respect to normal distribution. And what is this? I don't remember.
Can someone Google them? Normal distribution. So.
Why do you have 1 divided by W in the denominator?
Like, because
This is
POW.
log scale uniform prior.
yeah, POW is proportional to 1 over W. So plus, yes, it is plus expectation.
Log of W.
Yeah. I think it should be that's what W.
So it's a mean of log normal distribution, yes? Or log of absolute number of W.
Mhm.
Yeah.
So, I think we should simply believe that this expression does not depend on theta.
When, okay, later here we do the characterization trick, and the part that depends on theta, it can be brought outside, and like because theta is multiplied by everything else under the logarithm. And I believe the same term with theta will be in the entropy. And they just
Probably.
yeah, and we always have this term because the distribution is fixed, and we need to find such prior so that it destroys the term with theta over here, and the only way to do it is something like this. Okay. So all nice things about this prior, it is scale invariant, so we can multiply W by any number, and well, yeah, it still be constant.
What do you mean?
Like, so
I think the only way to say is that this is scale invariant prior.
yeah,
If we change the scale, the prior remains the same. This is the
Yeah.
property of such kind of a proper prior.
and
So this is
why-
analog of uniform distribution from minus infinity to plus infinity for the shift parameters.
Yeah,
So this is analogous distribution for scale parameters.
okay. So, and as for these scale divergence, it can be computed analytically because of this expectation, which is intractable, but we can approximate it accurately. So, in the paper, they provided two possible ways, the green one and the red one, whereas the exact value is the blue line. But they only used the values of alphas that are less than 1, so log alpha is less than 0. So they said that this green line is the lower bound for minus scale divergence, and the red line is a very accurate approximation.
Can you explain how did you give blue one?
The red one, I just took this expression and
Using Monte
sampled.
Carlo?
What?
Using Monte Carlo?
Yeah, sampled like tens of millions of epsilons and obtain this one. And then I guessed the shape of the curve and obtained a formula that fits very closely. So in this plot, it would be indistinguishable.
So I assume that we're able to compute this blue curve, which is exact, almost exact curve divergence.
Yeah, and it is, so here is, in the plus infinity, it is constant, and these ones are unbounded. And also, all these forms, they parallel large alphas because they increase when alpha increases. So, if it is possible, it would try to set alphas that are pretty high. Okay. So, let's go to experiments from the paper. The design was quite strange. So firstly, they said that let's clip alphas the value of 1, because if we don't do it, we experience some problems. Then they don't specify the training method for alphas and the way that so are the alphas shared for the whole network, or there are separate ones for a layer, etc. But okay, anyway, here the red curve is binary dropout, green curve is Gaussian dropout, and the blue curve is variational dropout. So this is the number of hidden units per layer. So these are different models, and it is just set error rate.
And how do they choose alpha in non-Bayesian methods?
I guess there was a formula which connects P to alpha.
Yeah, but how do they choose B?
From alpha.
No,
They choose parameters from previous articles reported by him and my.
so probably the power rate was set to 1/2.
Yeah.
Because this is all some default value.
Okay, and the best curve here, this one, it is even more interesting because they said, okay, it works pretty much the same as other methods, so sometimes better, sometimes worse. Let's divide the Kyle divergence by 3.
Right.
And yeah, just because to prevent underfitting. And they're
Justify
saying,
this division.
huh?
Justify this division.
Yeah.
Other prior or something.
Yeah, so the thing is, with this model, like the prior is fixed and it does not have any hyperparameters, so we can't change its power, its magnitude. So the division of Kyle division by 3 is equivalent to oversampling the data like 3 times. So they just made this regularizer like not so powerful.
Can you choose prior in terms of W so that you will obtain this division method?
Sorry again?
Can you choose prior on W so that you will obtain this division by 3 method?
Well, I don't think that there is any other prior that will correlate to the dropout procedure. So we won't have these correspondence that way.
Unfortunately, it is a quite common heuristic to rescale the Kyle divergence. Some other papers on weight uncertainty in neural networks do the same thing, but they have some flexible schedule which slightly, I think they they set the weight of Kell divergence to 0 and then increase it over time, something like that.
So we cannot exclude that probably the same results which prove dropout could be obtained if we set Kell divergence divided by 3 in the beginning, and then start gradually increasing the weight of Kell divergence and end up with Kell divergence whose weight is 1.
Yeah.
So maybe this is just hypothesis, and this would make the procedure strict, again fully Bayesian, good, and this heuristic, this division by 3, is only needed to perform better initialization and better training.
Yeah. So, so this is mixed results, and on CFAR, it works better without this heuristic. But alphas are still clipped, or 1 alpha, if there was only 1 alpha.
Inclusion error is like 30.
It is precise.
And it depends on the architecture.
Yeah.
They haven't used state-of architecture.
This was some principal address. I can look it up, but
It's on the section.
yeah. So okay, let's go to our experiments. So on the CFAR architecture, we try to replace the same thing. So we have binary dropout and Gaussian dropout, red and blue lines, and the green line is variational dropout at the beginning. So here the alpha was 1 for the whole network. Yeah.
0.2.
No, like all alphas was there was only 1 alpha.
Yes.
Yeah.
Layer
Oh, 1 alpha player.
per layer. Yeah.
Okay. So they were initialized by value of like 0.2, which is quite small dropout. And during the training, they almost got to 1, and because of this clipping heuristic, so it stopped there.
So it stopped at some limit point, and nobody can say whether this is an optimal point or the optimal lies somewhere further on when alpha exceeds 1.
Yeah, so the question was, can we remove these boundaries? So yes, we can, but as you can see, the red line is variational dropout networks. They start to, so the error rate starts to increase, and alphas go to very large values that correspond to dropout rates like 0.99, 0.95, and 0.61 on different layers.
And which are these layers?
So
The last layers.
the largest, I think, was the last layer.
The larger is the middle layer, and the smallest is the
Input.
finish one.
Last
Last one.
So does this mean that, well, this is a bit strange result to me, because this means that before I provide the answer, well, I prefer to have very large variance before I'm giving that.
The results, this result has very simple interpretation. This is simply poor local epsilon, and that's it. Because of course, when you have such dropout rates, this means that you completely nullify your network.
Yes, on the last layer.
Even on the intermediate layer.
No, I can understand why I may want to have large variance in the first layer, because I want to be resistant to some like noisy pixels in my data or something like that. But I can't understand how can I have any reasonable performance with such variances on the last layer.
Well, if the alphas are not shared per layer, if there are separate alphas for weights, it can use some sparse structure. Like half of alphas.
In the last layer, you have no so a lot of parameters. And for neural net, cheaper way make regularization smaller because it's pretty cheap. Because only 10 classes and
Yeah.
Well, actually, this picture only shows that potentially we can go beyond this constraint that alpha should not exceed 1. We can continue improving our variational dropout, but this particular result shows that we converge to poor local extremes.
Yeah.
And so our next steps will be
To maybe rescale the alphas or somehow change the optimization procedure so that we avoid the local optimum without the heuristic of placing alphas.
How does it work in this case in terms of error on CFR?
What?
in this case, error corresponds on random.
Okay.
Because
Okay.
so big values.
Once again, what is the difference between your procedure and Kinmark's procedure?
Yeah.
Here, the only difference is that we don't clip alpha and use different
Approximation for the log gaps.
And on the previous slide, the same, but
Yes.
alpha. I mean alpha.
description, yes, and it is exactly the same because like here they are very close.
So it's why in your experiments your dropout works better than usual dropout, and in Kingmas it's not better.
Like here is dropout, and here is variational dropout. It works better.
Ah, okay.
And why they have here 30%
Okay.
failure rate and then 45? Is it a different
Like,
architecture or what?
like here and then.
Yes.
Can I explain? If we try to repeat the experiment, we obtain much better quality using binary dropout, usually binary dropout. And I think that they manage his experiments not so good. Because we can repeat this experiment, and with usually binary dropout, we obtain much better results than reported in the paper.
Like this picture.
Yeah.
So you do something different from the experiment.
Mm.
Remember that they have like 30% and you have like half of a percent. No. Like CFAR, and the next is also CFAR. Yes. Your
This is
experiment.
unique. This is
I
fun.
understand,
and
but
this
your
is fun.
experiment is CFAR.
Yeah.
And you have like half a percent error.
or 45%.
45.
Is it
45 or I mean error in percents.
Means 45.
Could you explain?
Okay.
This is not point for
I can't.
So probably it is 45%.
If we will train usually dropout during 1000 epoch, we obtain better results. They
And what? Better than what?
better than reported in his article, but they nothing to say about number of epoch during training, and
What
they
about
just
variational dropout?
about variational dropout. Can you
Do
determine?
they have the same results with their blue curve?
No.
Because of number of epochs or what?
Because they describe the HFR experiment only in 2 lines. And they said nothing about settings of optimization method and something like that, and it don't describe at all.
Okay, can you clarify? You say that your results are better, but here I see like 25% of error, and at your graphic, see, I don't know what it is.
45.
45? Why is better?
Sorry, it's my error. We need to train our networks during the 1000 epoch in the file dataset.
So,
And so after that, quality of usual dropout method stays the same as they reported in variational dropout, for example.
Okay,
I
so
see.
you
The
will
question
have
was different.
10%, it's variety.
Yes, but if you want to
Okay.
Like what I'm trying to say is that this curve would be somewhere like here if we try to reproduce the results a lot.
Yeah.
can you
Maybe we should switch to Russian.
okay, if we train usually winner, если мы будем обычный dropout тренировать долго, мы будем лучше, чем самая низкая кривая. Вот.
Почему не рисовали график, где вы тренировали его долго?
Я прокосячил, я сказал, это накрыл.
А на второй вопрос, почему здесь у нас почему здесь у нас уровень ошибки 28%? То есть это из статьи. Следующая картинка ваша. Почему у вас 45?
Потому что тут не 1000 эпох, а 200.
Да.
Сказать, что
Она уже плохо
Ну, да, она падает очень сильно потом, через файлы.
Ну,
Она
видимо,
падает, она же почти стабилизировалась.
Learning rate изменили, упала.
Ну, окей.
Это вообще неожиданно.
Но
Натуральный график ни о чем не говорит.
Variational ниже, чем обычно, правильно?
Но тут преждевременно об этом говорить. Это как с самого начала.
тут
Нет, я понимаю, типа график существует в продолженном виде, когда я спрашиваю. То есть обычно dropout как тинговый variational, а variational ваш еще ниже.
Нет, variational наш не ниже, чем у Кельвина.
То есть у вас variational обычно одинаково.
Я не понял сейчас вопрос, смотри. В общем, ситуация какая? Они плохо натренировали обычный dropout, даже обычный. Если вот сравнивать дальше качество, какое оно будет через много эпох, вот, у них качество сильно, ошибка сильно завышена на обычных методах. У них реально получается разница между вариационным дропаутом хорошо обученным и их хорошо обученным, вот уже много эпох. Там получается 2%, дай бог.
Но она есть.
Да, она есть. Вот. И у нас она получается чуть-чуть меньше, но тоже есть.
Okay, let's continue in English.
Okay.
Yes?
Turn next few slides backward. Like, oh, here, the bottom, they have divergence.
Yeah.
It's minus have
Yeah, it's minus.
And you're trying to maximize it.
Yeah,
So this prior force you to increase out.
yeah.
Okay. And the first term is trying to decrease output because it likes small output for good training values, right?
Yeah, it's like smaller because the first like this term favors small variance. Ideally, if we don't have a second term, these will be delta functions.
Sorry, извините, в общем, я всем наврал.
Arseniy,
Простите, они
tell in
reported,
English.
they reported result on convolution architecture on TFAR. And therefore, the error rate much smaller. I have the same result. And those allowed, can you switch on our result? On convolution, on non-convolution architecture, on fully connected architecture, and this result have the same rate as main article reported and something like that. Sorry.
So there are different neural architectures.
Different architecture.
This is the only thing you should have asked.
Sorry,
There's different architectures, so the results are not comparable.
I a little bit confused.
One question. Is there a bigger result in given mass variation dropout on 200 epochs and 1000 epochs? Maybe it's not a question of quality, but a question of speed. What's the difference?
Because of the low variance of gradient, variational dropout сходится быстрее.
Yeah.
Yes, just. Okay, you said that their like green line is lower bound only than alpha.
No,
Low alpha versus
they said that the green line is the low bound everywhere, but it's not true.
Okay,
It
so am I right that it's a problem when we want our alpha to be 1 and 1? then it's not a low bound? Or
Like,
am I don't understand what is going on?
like they used this approximation, but they only used clipped alphas. We want to use non-clipped alphas, so we need new approximation. They also reported that this thing is a lower bound, like for all alphas. They didn't say that it is a lower bound for alphas that are less than 1. They said for all.
This is not true.
Yeah, but yeah, this is not true. It can be shown like on the paper.
Yeah, but this is some minor details.
Yeah.
So we
So
understand why
we-
they did it, because they have clipped alpha, so they're not interested in the behavior of lower bounds
Yeah.
with large alphas.
So what was the question? Okay. So, okay. Mhm. Yeah. So, in a way, what this prior does, this prior log scale uniform prior, it limits the precision of model weights. Instead of that, we can limit the precision of the neurons themselves, and like regularize the activations of neurons. So what it will give us, we will try to describe our data with inexact neurons, because it will be cheap in terms of regularization, in terms of our prior, and like other neurons. The only neurons that will be precise will be like only small amount of neurons should be precise. So what we want to do is to use log normal distribution on activations after the non-linearity, and like use it as a Australian distribution. So this is the future model.
So
And-
you finally decided to drop the idea to connect variational dropout and usual dropout and try a completely different thing, like other distributions, other models, etc.
No, not exactly. So first, there was justification that dropout corresponds to some kind of Bayesian regularization. So the question is, why to use this particular kind of approximation? From our point of view, this approximation is a bit awkward. That we are approximating posterior over the weights with the normal distributions, which are fully factorized, because based on the physical sense of prior distribution, which is improper log uniform distribution, it seems more natural to approximate posterior on the output of neuron rather than on the weights of neuron, and to use not a normal distribution, since we are dealing with a log uniform prior, but a log normal distribution. So this is normal distribution on the logarithms, because in the logarithmic scale there will be uniform distribution, and posterior can be normal distribution. So in the usual scale it will be log normal distribution. So this is the way. We can only do this after understanding of the Bayesian sense of dropout procedure. And we now understand that probably dropout is not the optimal regularization procedure. But we can conclude this only when we have realized that it is really Bayesian with a quite specific prior distribution and quite specific scheme of posterior approximation. So we can now change the way of approximating the posterior to a monoracial, well, at least from our point. And this is what we're trying to do next, right?
Yeah. So, okay. And now about an interesting application of variational dropout to linear models. So let me remind you about the RVM, the spectrum machine, which is a linear model for regression or classification. For regression, we have our output a real number, a linear model with like some noise, and our prior distribution is factorized Gaussian with different on the diagram. So, and this diagonal matrix A is the set of hyperparameters of our model. And the same thing for classification. We have logistic regression model and the same prior. So, okay. How do we train it? We compute the evidence, which is the denominator in the Bayesian quotient. So which is the integral of our likelihood times our prime integrated over W, and maximized with respect to hyperparameters. And an interesting thing occurs when we feed the hyperparameters. Some of them go to infinity. Each corresponds to like delta functions in our prior. Delta functions with the center on 0. And each forces our weights to be equal to 0. So we can just drop this weight, this feature. So this is a well-known model. And we tried to obtain similar results using variational dropout. So, in a sense, if we just strictly apply variational dropout and to this model and increase alphas, we still will obtain sparsity. So, the model will look like this. So, this is our likelihood. This is the objective, and so I guess it is not really relevant how this looks. But what is interesting that if we fix alpha, the exact gauge expression for W will look like this, and this expression is very close to what we have in RVM or ridge regression, etc.
Excuse me, could you please repeat once again from what consideration you obtained this objective?
It is just variational dropout objective. Like we have a neural network with
In
one.
variational dropout, we have a parameterized and non-parameterized prior on weights. Here's a different thing. You have a parameterized prior, which depends on alpha.
No, let's forget about the RVM for now. We have this likelihood. We have the prior from variational dropout. And we apply variational dropout, yeah. So, and we compare this model and RVM. So, and it can be seen that if alpha goes to infinity, it is here. The corresponding the corresponding coordinate of W will be equal to 0. And the corresponding marginal from the approximate posterior will be a delta function with center on 0. So, and we can do the same. And here we can do everything but the optimization of respect to alpha analytically. But we need gradient descent to optimize respect to alpha because we have Krell difference. So, and for logistic regression, things are pretty much the same. We have likelihood, and we need to compute expressions. These are the integrals from the expected log likelihood. And we can do this two ways. The first way is to use quadratures for these integrals. And the other way is just like in neural nets, we can just sample W from there and get a sample. Okay, so the experiments, we have synthetic data that is generated from the model for RVM. 100,000 objects, 100 features, and 90 features are irrelevant. So here is the mean square error with different mesh sizes. So here it is pretty much the same, and here the difference is not so big, but
Difference in the third digit.
yeah, it is not so big. Yeah. It is a scalable version of RVM. So, like, if we use double stochastic variational inference and apply it to RVM model, and then compute the corresponding expectations logically.
And remember that double stochastic inference is what we have considered in the last academic year.
Yeah. So, and so here is the time, and the interesting thing here is the relevance determination quality. We see that variational dropout found more than half of relevant features. Well, yes, the RVM found all of them, but still it is interesting that we have ARD effects with this model.
And potentially this opens ways for automatic setting the topology of neural network.
Yes.
Because if we set individual alpha to each neuron or to each weight, and since this variational dropout also has this ARD effect, then we could automatically remove some weights or some neurons.
Yes. And also, as the prior is fixed, its power is fixed, maybe we could increase its power and hope that variational dropout finds more features. It may be possible, but here we used just the fixed model that was given. And the same thing for logistic regression. Here, the accuracy for variational dropout is lower because this thing is more accurate. It uses quadratures, and here I think, yeah, the blue lines I used stochastic gradient. So the time is higher, we need more iterations, and the accuracy is lower.
Brilliant.
But still, then we have one iteration.
What is GKL?
DKL is, so I talked about it in the last semester. So we have the RVM model, and we use the DSVI, double stochastic variational inference, for this model. And then there are some expectations in the the gradients that we need to take, and we take them either analytically as here in linear regression or using quadratures.
So the answer is this is just scalable version of RVM.
Yeah.
That's it.
Yeah.
And variational dropout, RVM is not RVM actually, it's just a linear model with variational dropout, right? With the blue line.
Yeah. Yeah.
And why we have better relevance determination if we have oh my god, big watch.
It is an interesting question.
I mean, in this picture and in the previous picture, you have the same situation. The more patch you have, the better relevance determination you have. So
I would say the procedure hasn't converged to the small size of new mesh. And this is the answer. This is
what will we have if we have like very big batch, or we have like not stochastic gradient descent, but usual gradient descent?
We will get this. So there is a different setting. There are less objects, 1,000 of objects, but more features, 1,000 of features. And here both in both cases, variational dropout performed better. Like mean square error is less on the regression task, the accuracy is greater on the classification task. And the determination, so here it is not, oh, so it found most of them. Features, not all of them, but most of them. And here, it is a regression.
So in the previous slide, variational dropout was faster than you use live batch size.
It converts faster. Yes.
Can you explain why test error is smaller with relevance determination?
What?
Can you explain why variational dropout gives you smaller test error and higher and smaller relevance determination also than usual area? And both in this slide and 2 slides back. Yeah. Here.
Well, the relevance, so how I define relevance determination, like feature is relevant if the corresponding alpha is large. So for like these features, the alpha was not large, but still the feature was small. Like not 10 to the power of minus 10, as was the case with these features, but like 10 to the power of minus 5.
So relevance determination is the rate of features that you excluded.
Yeah, like in terms of alpha.
I thought that vice versa.
And can it happen that RVM also excludes some of relevant features?
So these situation was very rare. Like in all these experiments, no, there was no features.
No, but these are synthetic experiments which are ideal, specifically designed for RVM.
Yeah.
So these are data sets where RVM is the optimal choice.
Yeah.
And why do you choose like 10 in the power minus 10 as the threshold, not 10 in the power minus 5?
It is not a threshold. Like it is the point where alpha starts to stabilize and increase very slowly. Like logarithm of alpha is close to like 20, maybe 15, and the corresponding feature, optional feature, is something about 10 to minus 10 or 10 to minus 12, something like this. We can like increase alpha further, but as you can see, we won't gain much in terms of our lower bound. So even between like 8 and 10, there is not so much difference, which is just a
But am I right that if we take set like 10 in power minus 5, it's already it doesn't give us a lot to test our object.
Yeah. Other features was like about 1.
So it's like actually we don't need it.
Yes.
So yeah.
So actually there is like 100% the next year.
So yes, but we wanted to like exclude them not by the value of theta, but which is kind of a heuristic where we put this threshold by the value of alpha, and they go to infinity, then we can remove it.
So this is perfectionist.
To continue, I got this question. As far as I understand, both methods maintain a normal distribution for each weight, for each feature, right?
Yeah.
So just to, well, and we need some more, probably we need some more stable variable to estimate what we call relevancy, or the amount of relevant features. Can we do the following? Can we select some very narrow Gaussian located at 0 with 0 mean, and compute, let's say, the KL divergence of each of these normal distributions to this Gaussian. Then they will be compared in the same way. because these two methods express relevancy in different ways. And when we decide if either method has chosen a particular feature as relevant, well, we need some more uniform, some more introduce in the same way somehow, without thresholds.
I think there may be a problem because if you have two very narrow coefficients, they are close to each other, but like not exactly overlapping, but the curl divergence will be very high. So, which is, I don't know if it is an adequate measure.
And again, you will still need some kind of threshold to compare this.
No, I can just sum. No. I can what I can do. I can sum these curl divergence for each feature for both methods and compare them by just as numbers. I wouldn't be able to compute any rate or percent, something like that. I would compare just two numbers.
To define what? Which method is better?
Which method is better? Because right now it looks like it really depends on the value of threshold.
Sure.
And on interpretation of relevancy.
This is not our goal. We're not comparing what method is better. We're showing here that variational dropout prior really leads to ARD effect, automatic irrelevance determination, and it can detect irrelevant features and it can remove from the model. So it has properties which are quite similar to the properties which RVM has. So this is the main motivation of this experiment.
Okay, I see. But your conclusion also depends on the definition of relevancy.
No, but we see that actually variational dropout can detect irrelevant features.
So the idea is just to show that it makes sense to use it for the.
Because if it makes sense, then we will try to transfer it to deep neural networks, and we will try to assign individual power rate or individual alpha to each neuron or to each weight. We can expect the same behavior. And the same behavior means that some of the weights will be set exactly to 0, or some of the neurons will be exactly removed from our neural network. And by doing this, we can, at least in theory, define the proper structure of deep neural network.
Yeah, and also there were some quite promising results from Max Welling's former master student. On his master's thesis, he experimented with neural networks with the spike and slab priors, and there was sounds positive.
A friend of mine did the same thing. He could set half of weights to 0.
Yeah, so maybe
but
half of weights is not very much.
But what if we just take an IRT for neural nets? Can we do this?
So we try to do it.
The question is, we can. The problem is that that Bayesian inference is not more tractable, unlike our RDM case. So we'll need to design some kind of approximate Bayesian inference procedures. And again, it's not clear what should it be. What should it be relational posterior? Maybe it should be the same. Maybe not. For the report, we will know more or less what is the family of approximate posterior distributions. For ARD prior, we do not. And of course, the problem is that the number of hyperparameters will increase. So we'll have hyperparameters for the prior, individual parameters, and we'll have also relational hyperparameters for posterior distribution. So in variational dropout, we do not need hyperparameters for prior distribution. Prior is just fixed. And prior has some physical limitation. But well, of course, we could try.
Yeah, other questions?
Is it the last slide?
What?
Yeah,
today.
No, so I don't say do you know anything about application of variational dropout to RNNs?
Joe?
To current neural networks?
No.
I just heard that there seems current neural networks variational dropout is much better than just dropout. But I don't know.
Is there some kind of a paper?
Yeah. But I didn't read that. read the article and test it better.
Okay.
So to be great, we should send it to
Yeah.
Dmitry, let's say.
And for me.
I can send it to the
To the whole group. Okay,
Yes.
Have you compared this relevance, determination, accuracy? Have you measured the relevance, determination, accuracy of like a one realization?
No.
Well, you should, because maybe it's just as well as your variation dropout.
Well, I think there was some combinations between the RVM and also, but well, here you can see variation dropout. The relative determination is worse than RVM, so probably in these terms, probably it will be worse than L1, but
Maybe if you bring back that KL divergence theorem with a standard normal distribution
like
prior, maybe then it will naturally want to regularize the set base to 0. And it is done in RVM. So yeah, maybe if you bring back the standard normal prior, then it will regularize much better because it will want to do that.
funny thing with funny thing with a normal prior is
Yes, please.
So this is what we do.
so if we have a normal prior, then there will be in the lower bound there will be a nested term 1 over theta, and which is bad.
Why?
So like the interesting case for us will be where thetas are close to 0. And here we have the term 1 divided by theta, and the gradients will explode. Which will be. So,
But then you can use maybe this log scale for it, as you mentioned.
Yeah, so right now I'm experimenting with some other application for sequential learning, and here we have the normal priors, and yeah.
Any other questions? So to conclude, as I told you in the beginning, it's just a tiny step towards combining deep learning and Bayesian models. And I would say that I would make some analogy with the boosting techniques, which were designed by engineers in the beginning of the 90s. And boosting was purely heuristical procedure. It corresponded to common sense, but actually nobody could understand why it works. Why it works so nice. And later, scientists came and they could justify the procedure, and it appeared that this is not heuristic. This is just greedy maximization of some well-defined criteria. And after they have done this, it appeared that we could define other criteria, which are also reasonable, and we will come up with the different boosting schemes. And this is the way how different boosting schemes have appeared. So probably with dropout, the situation is pretty much the same. So there was purely heuristic procedure, dropout. Then it was, again, heuristically justified to go with dropout, but still heuristic. And now we have, this is a result of December of last year, we have a Bayesian justification. So now I understand that actually this is a special, quite rough approximation of a special kind of regularizer of this way, of this kind. And the interesting thing is that this particular prior distribution has physical interpretation. So this is not just some arbitrary prior distribution. It has interpretation. This is a log uniform prior distribution, so it has interpretation in terms of, say, significant digits of the values of weights. Well, it's not easy interpretation, but it exists. This is one good news, and another good news that if we somehow are not satisfied with this prior distribution, we can always set a different prior distribution. Then consider the problem of maximization of lower bound, and we'll obtain completely different stochastic scheme, which doesn't look like dropout. It will be completely different. But it will do approximately the same thing, but just with a different prior distribution. So this way would be impossible without understanding of what is dropout. The dropout is actually a special kind of Bayesian regularization. After we have understood this, we can modify regularization, but whatever we want, and to design different training procedures with different properties. So this is quite interesting intuition, and it's quite useful to understand. Probably, this is my forecast that in a few years we'll see the same justification or half of Bayesian justification of Bayesian normalization. Because now people are using Bayesian normalization as a kind of regularization. This is again a heuristic procedure, so it corresponds to common sense, but it doesn't have some theoretical justification. And maybe again people will find that this is some rough approximation for some Bayesian procedure, and after this we'll be able to design different modifications of different regularizers, and Bayesian normalization will be just a very tiny particular case of a much more general technique. But this is for my dream. Okay, so let us thank the speaker. But for the future speakers, I would ask them to better understand and to be able to better explain all experimental results which are included in slides. Otherwise, you either include some experimental results, and then you should be able to understand, to explain everything, to answer any question on the experiments, or you just remove it from the presentation. Just one more note. Our next seminar will be in 2 weeks, not in 1 week, because next week there'll be Christopher Lambert's talk. It will be on Thursday. Thursday is 8th of September. So we will cancel our seminar, and I would call all students and PhD students from my group to visit Christopher Lambert's talk. Yeah, at Yandex. At Yandex, but on Thursday. So, and we meet again on Friday, but in 2 weeks.